Okay, so for the example on slide 6 of lecture number 8, we have a problem that says, suppose we have 10 nanocoulomb point charges which are located on the corners of a square of side 10 centimeters. Locating the square in the xy plane with one corner at the origin, right here, and then the other corner at the point P, which is at 10 centimeters, 10 centimeters, and 0, right? So we're in xy plane, so it's 0 for the z coordinate. Now we want to find what is the total force acting on the point P. Well, this is a problem in which we can use superposition. So basically we can say that due to Coulomb's law, we'll have a force exerted from the first charge onto the third charge, the second charge onto the third, and the fourth onto the third. And each can be evaluated independently, right? And then sum all of them up. So this equation right here represents what Coulomb's law says and what superposition says. It basically says that each one of these are acting independently and we can sum them up. So the question is, we know what Q3 is, we know what Q sub I is for any I, that's equal to 10 nanocoulombs. The only difference in this is what is the R vector and what is the magnitude of the R vector. Once we solve that, that's basically all we have to do for the problem. So let's look at 1 to 3, okay? So R 1 to 3, we simply take the x, y, z coordinates at 3, subtract them from the x, y, z coordinates at Q1, and that's going to give us our vector. So it's pretty clear we have 0.1 ax plus 0.1 ay, and then the z component is just 0 minus 0, okay? So we calculate the magnitude, and I'll do it for this first one, but the other ones I'll just write the result. What we do is we sum the square of all the components and take the square root. So that gives us 0.1414 meters, right? Okay, we have R13. Now the question is to get R23, okay? So 23, we go from here to here. Well, you can see in this point, we subtract the x components, we just get 0. We subtract the z components, we get 0. The only component we're going to have is this y component. So it will be 0.1 ay. And right here we only have one component, so it's clear that its magnitude is simply equal to 0.1. For R 43, we'll do the same thing, except this time we'll see that this is only going to have a x component because we have 0.1 for y, 0.1 for y, 0 for z, 0 for z. So we get 0.1 ax, and this has a magnitude equal to 0.1. Okay, so now we have all of the information that we need. We have for I equals 1 through 4, excluding 3, we have the RI3 vector, and then we have the magnitude of each of those. So we can simply plug this into a formula, and we'll say the force on P is equal to Q3, which is 10 nanocoulombs, so 10 times 10 to the negative 9, times 4 pi times the permittivity of free space, 8.854 times 10 to the negative 12 farads per meter. And then we're simply going to add each one of these Q's times the RI3 vector divided by the I3 magnitude. But if we look at this, for Q1, Q2, Q3, and Q4, it's always the same. It's always 10 nanocoulombs. So we can just pull that term out and then square this right here. So just pulling that out, we can square this, and then we're just summing up the vectors. Okay? So here's what we have. For R13, we have 0.1 ax plus 0.1 ay, and we're going to divide that by the magnitude cubed, right? So we have 0.1414 cubed. Okay? And we're going to add that on to this vector here. So 0.1 ay divided by 0.1 cubed, and add it on to this guy right here, 0.1 ax divided by 0.1 cubed, and that's all of our vectors. Now at this point we simply need to calculate what the final answer will be, and when we do that we'll see that we get 121 0.7 AX plus 121.7 AY. And since this is a force, it will have units of newtons. These are times 10 to the 6, so we'll say micronewtons, okay? So let's think, does this make sense? Well, all of these are the same charge. They're all like charges, so it's a force of repulsion, right? So this force will be exerted in this direction. This force will be exerted in this direction. So the resultant of those two will have a force in this direction because components will cancel out. But then we can see that Q1 will also exert a force in this direction. So we have a force that is equal component in the X direction as it is in the Y direction. And that makes sense graphically through what we have right here. Okay.
Okay.
Thank you, Bill. Appreciate that.